A rock between Mars and Jupiter is worth more than the whole global economy. No spacecraft has ever reached it. It won't arrive for 3 more years. Then engineers pointed its cameras at a totally different planet instead, just to test the gear. The readings that came back do not match what anyone expected the target to be. The asteroid nobody can actually mine. The asteroid is called 16 Psyche, and it sits in the main asteroid belt, roughly 3 times farther from the Sun than Earth is. It was discovered in 1952 by Italian astronomer Annibale de Gasparis, who named it after the Greek goddess Psyche. It ranks as the 10th most massive object in the asteroid belt and the largest known object made mostly of metal, measuring roughly 140 miles across at its widest point. Scientists classify Psyche as an M-type asteroid, a category defined by how it reflects sunlight, a pattern that closely matches the surface of iron meteorites found here on Earth. It is not the only M-type asteroid out there, and it is not even the most theoretically valuable. A different asteroid called 511 Davida, roughly similar in size, has been given an estimated value as high as $27 quintillion in some of the same rough calculations used for Psyche, simply because it is slightly larger and assumed to carry a comparable mix of metal. Neither number changes anything about how these objects are actually studied, since no mission currently exists to visit Davida, and Psyche remains the only M-type asteroid humanity has ever sent a dedicated spacecraft to examine up close. That metal content is exactly why Psyche keeps showing up in headlines with almost absurd dollar figures attached. Based on early estimates of its size and metal content, some researchers calculated that if Psyche were somehow hauled back to Earth and every scrap of iron, nickel, gold, and platinum inside it were sold at current market prices, the total could reach $10 quintillion, or 10 quintillion. Other estimates, using slightly different assumptions about how much of the asteroid is actually metal, have put the number as high as 700 quintillion or as conservative as 100,000 quadrillion dollars. Every one of those numbers falls apart the moment anyone tries to act on them. Lindy Elkins-Tanton, the planetary scientist at Arizona State University who leads the Psyche mission, has said directly that dragging a giant metal object back to Earth raises an obvious question nobody has a good answer for, which is what anyone would actually do with it once it got here. Dumping that much gold, platinum, and nickel onto global markets all at once would collapse the price of those metals long before anyone turned a profit, which is exactly why serious economists treat the quintillion-dollar figure as a thought experiment rather than a real number. NASA is not sending a spacecraft to Psyche to mine it. The real reason is stranger and, in a different way, more valuable than any of those imaginary dollar signs. And it starts with a spacecraft that almost didn't make it off the ground on schedule at all. The spacecraft already on its way. The Psyche mission was originally chosen by NASA back on January 4th, 2017, as part of the agency's Discovery program, a line of lower-cost, competitively selected missions, each led by a single principal investigator, in this case, Elkins-Tanton. The team originally aimed for a July 2022 launch. That plan fell apart just weeks before the launch window opened. On June 24th, 2022, NASA announced it was scrapping the 2022 attempt entirely, after mission leaders determined that critical guidance, navigation, and control software had been delivered too late for the team to properly test it before launch. Lori Glaze, director of NASA's Planetary Science Division at the time, said the project had overcome nearly every other challenge building a spacecraft during the pandemic, only to get stopped by this one final software problem. Because of how Earth's and Psyche's orbits line up, missing that single 2022 window pushed the earliest realistic launch dates all the way out to 2023 or 2024, and it pushed the earliest possible arrival at the asteroid from 2026 out to 2029 or later. That single delay had a real casualty. Nobody outside the space community paid much attention to. A separate NASA mission called Janus, built by Lockheed Martin and led by the University of Colorado Boulder, had been scheduled to ride along on the same Falcon Heavy rocket, using 2 small satellites to study a pair of binary asteroid systems near Earth. Once Psyche's launch slipped to October 2023, the trajectory that rocket would follow no longer matched what Janus needed to reach its original targets, and NASA formally pulled the mission off the manifest entirely. The 2 finished Janus spacecraft ended up sitting in storage at Lockheed Martin with nowhere to go, a strange fate for hardware that had already been fully built and tested. Years later, mission scientists, including Janus principal investigator Dan Shiras, began exploring whether the shelved spacecraft could be given a second life entirely, potentially repurposed for a future flyby of Apophis, a well-known near-Earth asteroid making a historic close pass by our planet in 2029, using a Lagrange point detour and a lunar flyby to set up the encounter years in advance. Nothing has been finalized, but it is a reminder that a single software delay on one mission can ripple outward and reshape the plans of an entirely different one. The delay also affected the Deep Space Optical Communications Experiment, or DSOC, built to test whether a laser beam could carry data across deep space far more efficiently than traditional radio signals. NASA eventually settled on an October 2023 launch date, and the Psyche spacecraft finally lifted off from Kennedy Space Center on October 13, 2023, riding a SpaceX Falcon Heavy rocket. Once in space, the DSOC experiment quietly became one of the most successful side stories of the entire mission. On November 14, 2023, it achieved what engineers called first light, successfully exchanging a near-infrared laser signal carrying test data across nearly 10 million miles. The following month, on December 11th, 2023, it beamed the first ultra-high-definition video ever sent from deep space, transmitted from 19 million miles away at a peak rate of 267 megabits per second, a data speed that would be impressive even over an ordinary home internet connection, let alone across that kind of distance. The demonstration kept setting new distance records through 2024, eventually commanding the instrument and confirming laser tracking from more than 288 million miles away, roughly 3 times the distance between Earth and the Sun. DSOC completed its final scheduled pass in September 2025, nearly 2 years after launch, having proven that laser-based communication really could work reliably across the kind of distances future deep space missions will need to cover. Unlike a normal rocket-powered spacecraft, the Psyche orbiter itself moves using electric ion thrusters, a propulsion system that throws out charged particles of xenon gas to produce a slow, steady acceleration rather than one big burst of thrust. NASA has pointed out that a traditional chemical propulsion system would have required packing the spacecraft with roughly 15 times more fuel before launch, which simply was not practical for a mission covering this kind of distance. The engines are powered by 2 enormous solar panels, since the spacecraft is still close enough to the Sun for that to work. Unlike missions headed toward the outer planets, the spacecraft first activated its 4 Hall effect thrusters in May 2024, more than 7 months after launch, after spending that time simply coasting on the momentum from its initial rocket boost. Getting all the way to the asteroid belt on ion power alone takes patience, which is exactly where Mars came into the plan. Rather than fighting gravity the whole way, the mission team built in a stop at Mars specifically to steal some of its momentum for free. Before that stop ever happened, though, the mission ran into a problem that had nothing to do with software or planning and everything to do with a single, stubborn valve. A mechanical scare along the way on April 1st, 2025, roughly a year after the spacecraft first switched its engines on, onboard sensors detected a sudden pressure drop in the line carrying xenon gas to the thrusters, falling from about 36 pounds per square inch down to roughly 26 pounds per square inch. As designed, the spacecraft automatically shut its propulsion system off in response, since running the thrusters with an unexplained pressure drop risked further damage. NASA confirmed the issue publicly later that month, and mission engineers spent weeks studying telemetry data to figure out exactly what had gone wrong nearly 150 million miles away, with no way to send a technician anywhere near the actual hardware. The good news built into the spacecraft's design was that this exact kind of failure had been anticipated. Psyche's propulsion system includes two identical xenon fuel lines, specifically so the mission would have a backup if one ever failed. By late May 2025, engineers had traced the problem to a faulty part inside a valve on the primary line, a component responsible for managing how much propellant flows through to the thrusters, which had partially obstructed the flow. Rather than trying to repair a part nobody could physically touch, the team simply switched operations over to the spare line entirely, leaving its valve open going forward to avoid the same failure happening twice. Louise Proctor, director of NASA's Planetary Science Division, told colleagues at an April 2025 meeting that the JPL team was doing excellent work isolating exactly which component was responsible, even from that distance. By early June 2025, the backup line was confirmed operating normally, and the spacecraft resumed thrusting on schedule, having lost only a couple of months rather than jeopardizing the entire mission. That kind of quiet, methodical troubleshooting across tens of millions of miles is not the part of space exploration that usually makes headlines, but it is exactly the kind of problem solving that determines whether a mission like this actually survives long enough to reach its target. With the propulsion system back online and the spacecraft healthy, the mission moved forward toward its next major milestone, the Mars flyby that had been part of the plan since well before launch. The flyby that wasn't just a speed boost. On May 15th, 2026, the Psyche spacecraft passed within about 2,864 miles of the Martian surface, using the planet's gravity to add roughly 1,000 miles per hour to its speed and shift its flight path by about 1 degree relative to the Sun, all without burning a single drop of onboard propellant. Don Hahn, the mission's navigation lead at JPL, said the team had confidence in their calculations going in, but still found it exciting to watch the real-time radio signal data confirm the maneuver had worked exactly as planned. Following the flyby, the spacecraft is now locked onto a direct path toward the asteroid, with arrival still expected in the summer of 2029. Because the spacecraft was going to fly past Mars anyway, the mission team decided to squeeze real science out of the encounter, rather than treat it as a pure engineering maneuver. The multispectral imager, a pair of identical cameras built to eventually photograph the asteroid's surface in different wavelengths of light, spent the whole month of May capturing images of Mars, including a striking mosaic of the double-ring Huygens crater, a feature roughly 290 miles across, sitting in the planet's heavily cratered southern highlands. The spacecraft's magnetometer, designed to eventually measure Psyche's magnetic field, picked up a sharp spike as it crossed Mars's bow shock, the boundary where solar wind slams directly into the planet's magnetic field. Ben Weiss, who also leads the magnetometry work, said the flyby validated how the instrument performs under real, dynamic conditions, while also revealing details about how Mars's own magnetic environment behaves. The gamma ray and neutron spectrometer, the instrument that will eventually help identify which elements sit on Psyche's actual surface, also got a full test during the pass. As cosmic rays strike a planet's surface, the elements present absorb some of that energy and release it back out as neutrons and gamma rays at specific energy levels the instrument can read. Engineers used the Mars flyby to confirm the spectrometer was working exactly as designed, well before it will ever matter for the real target. The spacecraft even caught sight of Mars's two small moons, Phobos and Deimos, adding a bonus set of images that nobody had originally planned to capture. Mission scientists later said they had not expected any major new discoveries about Mars itself, given how extensively other missions have already studied the planet. But the unique vantage point still let the team compare their instrument readings against decades of existing Mars data as a real-world sanity check. None of this changes anything about Mars itself, since the planet has already been studied in extraordinary detail by other missions, but it gave the Psyche team a full working rehearsal of every instrument they will depend on 3 years from now. That rehearsal matters more than it might sound, because recent findings back on Earth suggest the asteroid waiting at the end of this journey might not be exactly what anyone originally expected. If you're finding this one interesting, hitting subscribe means you won't miss the next mission update. Why scientists already doubt the metal world story. For decades, the leading theory about Psyche was straightforward. Scientists believed it was the exposed metallic core of a much larger planet that formed early in the solar system's history, then had its rocky outer layers stripped away by violent collisions, leaving only the dense metal center behind. That theory was based mainly on how sunlight reflects off the asteroid's surface, a pattern that closely resembles iron meteorites found here on Earth, along with millimeter wavelength observations suggesting a metal content of at least 20%. That comparison to iron meteorites is worth explaining, since it is the whole foundation of the original theory. When a planet or planetesimal is large enough, gravity and heat cause it to separate into layers, with heavy metal sinking toward the center to form a core, while lighter rock floats up to form a crust and mantle, a process scientists call differentiation. Every iron meteorite ever found on Earth, including famous specimens like the Cape York meteorite recovered in Greenland and the Hoba meteorite discovered in Namibia, the largest single meteorite ever found, is believed to be a fragment of exactly this kind of ancient metal core, blasted off some shattered planetesimal billions of years ago and eventually falling to Earth. Many of these meteorites even show a distinctive crystal pattern called the Widman-Staten pattern when cut open and polished, a banded structure that only forms when molten iron and nickel cool extremely slowly over millions of years, exactly the kind of cooling that would happen deep inside a planetary core rather than near its surface. Psyche's reflected light signature looked close enough to these meteorites that scientists spent years assuming the asteroid was simply a much larger, still intact version of the same kind of object. In August 2024, a research team led by Stephanie Jarmack at the Southwest Research Institute used NASA's James Webb Space Telescope to look more closely at that surface, and the results complicated the simple metal core story considerably. Webb's instruments detected a clear signature of hydroxyl molecules, essentially a form of chemical hydration, on Psyche's surface, the kind of signal typically associated with certain types of carbon-rich meteorites, rather than pure exposed metal. The team's published findings, which appeared in the Planetary Science Journal, described two separate detections of a specific absorption feature strongly associated with hydroxyl and water, resembling signatures normally seen in carbonaceous chondrite meteorites. One of Webb's instruments, called MIRI, did not find a matching signal for actual water ice at a different wavelength, so the team stayed cautious about how much water, if any, might exist there. Some analysis of the same data even suggested the hydroxyl signature could be a form of rust, meaning oxygen and hydrogen bonded directly to metal on the surface, which would be a strange thing to find on an object many scientists had assumed was a bone-dry chunk of ancient planetary core. That single finding reopened a debate that mission scientists are still actively working through. If Psyche really is a mostly metal object, how did any hydrated material end up on its surface in the first place? One leading idea points to a massive crater near the asteroid's south pole, possibly left behind by a collision with a smaller, water-bearing object at some point in the distant past, which could have deposited hydrated minerals across at least part of the surface without changing what lies underneath. Researchers now plan to study that southern crater closely once the spacecraft finally arrives, since mapping exactly where the hydrated material sits could help settle whether Psyche started out purely metallic or has always been a mixed body of both metal and rock. Other competing explanations under consideration include the idea that Psyche formed as a metal-rich object from the very beginning, rather than through a violent stripping event, or that repeated impacts with other asteroids gradually built up a mixed composition of metal and rock over billions of years. Every one of these open questions is precisely why NASA is sending a spacecraft there at all, rather than simply trusting the picture built from telescopes on the other side of the solar system. For context, this would not be the first time a spacecraft visit completely rewrote what scientists thought they knew about a large asteroid belt object. NASA's Dawn mission, which orbited the protoplanet Vesta, starting in 2011, and then traveled on to orbit the dwarf planet Ceres, starting in 2015, revealed both bodies to be far more geologically complex and differentiated than ground-based telescopes alone had ever suggested, including surprising evidence of ancient volcanic activity and buried ice. Psyche's own science team has pointed to that precedent directly, arguing that only a dedicated orbiter, flying close enough to map surface composition and measure a magnetic field directly, can ever truly settle a question this complicated. NASA has run a handful of other asteroid missions in recent years as well, including OSIRIS-REx, which touched the small carbon-rich asteroid Bennu in 2020 and successfully delivered a physical sample back to Earth in 2023, and the ongoing Lucy mission, launched in 2021 to survey a series of ancient Trojan asteroids sharing Jupiter's orbit. Psyche stands apart from both of those, since it targets the single largest confirmed metal-rich body in the entire asteroid belt, and it is designed purely to orbit and measure, rather than to touch down or return any material at all. How the spacecraft will actually study the asteroid. Assuming everything goes according to plan, Psyche is expected to be captured by the asteroid's gravity around July 2029, with orbital science operations beginning that August. From there, the mission unfolds across 4 distinct orbital altitudes, confusingly labeled A, B, C, and D, which do not run in alphabetical order. Instead, the sequence is built entirely around how much sunlight will be striking different parts of the asteroid at each point during the roughly 26-month prime mission, since the onboard cameras need enough light to actually photograph the surface in useful detail. The spacecraft begins in Orbit A, the highest and widest altitude, primarily used to measure the asteroid's spin axis and overall shape before descending closer. From there, it drops into the first part of Orbit B, focused on mapping topography and geology across at least 80% of the surface, while continuing to track gravity and magnetic field data. Because the amount of sunlight hitting the asteroid keeps shifting as it moves along its own orbit around the sun, the mission plan actually splits Orbit B into 2 separate segments, informally called B1 and B2, executed months apart once favorable lighting conditions return. In between those two segments, the spacecraft dives down into Orbit D, the closest of all four altitudes at roughly 47 miles above the surface, before climbing back out to the mid-range Orbit C to complete its highest priority gravity and magnetic field measurements. The mission has also built in an extra 67 days of margin at the very end of the prime mission, specifically to absorb any unexpected delays or extend science observations if everything is running smoothly. It is an unusually complicated flight plan compared to a simple circular orbit, but it reflects just how much the team is trying to extract from a single spacecraft that will likely never get a second visit to this particular asteroid in most of our lifetimes. What $10 quintillion actually means and why it doesn't. Coming back to that headline number helps explain why NASA has never once described this as a mining mission. The estimate of $10 quintillion, along with the higher and lower versions of it that circulate online, comes from multiplying Psyche's estimated mass by rough guesses about how much of it is iron, nickel, gold, platinum, and other valuable metals, then pricing all of that material at whatever those metals happen to sell for on Earth right now. That math technically checks out on paper, which is exactly why the number keeps getting repeated across headlines and social media posts for years without much scrutiny. It also completely ignores the fact that nobody currently has any realistic way to mine an object 280 million miles away, let alone transport that much material back to Earth in one piece. This is not a purely theoretical problem either. A wave of private companies, including one called Planetary Resources and another called Deep Space Industries, launched in the early 2010s, specifically chasing the dream of asteroid mining. Backed by investors and even a few small technology demonstration satellites placed in low Earth orbit. Both companies eventually ran out of funding and were absorbed by other firms years before ever coming close to reaching an actual asteroid, let alone extracting anything from one. Their struggles illustrate exactly why the quintillion-dollar figure attached to Psyche has never translated into a serious commercial mining proposal, since even the basic engineering and financing hurdles for reaching a nearby asteroid have proven far harder to clear than early enthusiasts expected, long before anyone gets to the harder problem of an object sitting all the way out in the main asteroid belt. Even setting aside the transportation problem entirely, flooding global metal markets with a quintillion-dollar supply of gold and platinum overnight would crash the price of those metals almost instantly, since their entire value depends on scarcity. A metal that suddenly becomes as common as gravel does not stay expensive for long. Elkins Tanton has pointed out that even grabbing a large metal fragment and hauling it back home would leave scientists facing an obvious follow-up question, which is what anyone would actually do with a piece of asteroid that size once it landed. NASA's actual funded budget for the mission, including development, the launch itself, and years of operations, runs to roughly $1.2 billion, a real, modest figure next to the almost cartoonish sums attached to the asteroid's theoretical resale value. The real reason NASA is spending that money has nothing to do with striking it rich. Objects like Psyche represent leftover material from the earliest days of planet formation, more than 4.5 billion years ago. Earth's own metal core sits roughly 1,800 miles beneath the surface, buried under so much rock and pressure that no drill built by humans has ever come remotely close to reaching it. Psyche, whatever its exact origin turns out to be, offers scientists a rare and much cheaper way to study material like that up close without having to drill through an entire planet first. That scientific goal is also exactly why the mission's actual timeline matters more than any dollar figure ever could. What happens next? With the Mars flyby now complete and the propulsion system running normally again on its backup line, Psyche is on a direct course toward the asteroid belt, with arrival expected in the summer of 2029. Once it gets there, The spacecraft will not land or touch the surface at all. Instead, it will settle into the sequence of increasingly close and carefully timed orbits described above, using its cameras, magnetometer, and gamma ray and neutron spectrometer to map the surface, measure the magnetic field, and identify exactly which elements make up the material below, with particular attention paid to that hydrated crater near the South Pole. Once the spacecraft is finally close enough to study it directly, that plan means the honest timeline looks like this. The spacecraft launched in 2023 after a year-long software delay that also grounded an entirely separate mission, tested its instruments on a real planet for the first time in May 2026, following a scare with its own fuel valves the year before, and will not begin its actual science mission at the asteroid itself until 2029. Nobody, not NASA, not the mission scientists, and not the media outlets that keep repeating the quintillion-dollar figure, has any evidence that anyone has physically touched, sampled, or mined this asteroid. What has happened so far is a spacecraft slowly closing the distance across billions of miles, using every opportunity along the way, including an unplanned decade-old planet it was only passing by, to make sure its instruments work exactly as intended before the real target ever comes into view, the verdict. Psyche has not been touched, and it will not be touched even after the spacecraft finally arrives in 2029, since the mission is built entirely around orbiting and observing, rather than landing or collecting samples. The $10 quintillion figure attached to the asteroid is a real calculation based on real estimates of its metal content, but it describes a value that could never actually be realized here on Earth, since mining and hauling that material back is not physically possible with any technology that exists today. Past private ventures already proved as much, and dumping that much metal onto the market would collapse its price regardless. What did just happen in May 2026 was a real, confirmed gravity assist past Mars that boosted the spacecraft's speed, tested every instrument it will rely on for the actual mission, and delivered genuine new images and data along the way, arriving only after the mission survived both a year-long software delay before launch and a stuck fuel valve along the journey itself. Combined with the 2024 discovery of hydrated minerals on Psyche's surface, the honest picture of this asteroid is far more interesting than any headline number. A leftover fragment from the earliest solar system that might not be the simple metal core scientists once assumed, with the real answer still 3 years away. If you enjoyed this one, make sure to subscribe, and I'll see you in the next one.